Today we're going to talk about, or in this session, we're going to talk about the analysis of variances covered in Chapter 12 of the textbook. And the source material for this that I'm going to start off trying to use is about 20 minutes long, so I suspect that we'll at least have 3 of these short 10-minute videos. So again, we'll get started and then we'll break in as needed to make corrections and supplement the current information.
Analysis of variance is used to compare more than 2 groups. You can use a t-test to compare 2 groups, and then the analysis of variance would be 3 or 4. It's generally called a one-way analysis of variance. So that brings up the fact that if there's a one-way, then there's also a 2-way or a 3-way or a 4-way, and we'll discuss that at the end of this PowerPoint. Analysis of variance. The basic idea is that if the variance between the samples is greatly larger, significantly larger than the variance within the samples, then there is a difference between the samples. You're going to have variability, and as the variability within the sample is about the same as the variance between the samples, then there's not much difference. And we'll have a demonstration at the end of this PowerPoint, towards the end of this PowerPoint, that'll help you to see that. If the variances are statistically the same, then there's no difference. And the F distribution is going to be used to statistically measure the difference. As you'll recall, the F distribution and the chi-square distribution are 2 that are not symmetrical. The uniform, the normal, the t distribution, those are symmetrical. But the F distribution and the chi-square are greatly skewed. When you see that in a plot, you'll understand that. So why don't we just use multiple t-test? The reason is because it increases the probability of making a type 1 error. Remember, the type 1 error has to do with the confidence that we have in the results. For example, if we have an ANOVA to test that mean 1 is equal to the mean 2 is equal to the mean from sample 3, then since it's an ANOVA, we only need to use the one test. But if we do that same test with a t-test, then we have to compare the mean from the first 2 samples to the mean to the second 2 samples, and then we have to compare the first and the last sample. So that requires 3 tests, and 3 tests at the 0.95 level. You raise the 0.95 to the 3, that actually gives you an 86% level of confidence instead of the 95. And so you can see that if there's 4 groups or 5 groups, then the problem is even worse. So the analysis of variance is the right way to do this instead of doing multiple t-tests. From the analysis of variance, it will tell us that a significant difference exists, but the analysis of variance does not tell you where the difference is. Whether the difference is between groups 1 and 2, or between groups 2 and 3, or between some of the other groups. It tells us a difference exists, but it doesn't tell us which one of the means are different. So we have to use a multiple comparison test. There are several of those out there, the Chaffee, the Tukey, the Bonferroni. That's a little bit beyond the scope of this textbook, but those are available. So let's look at the calculations here. You can see that The first thing that we have here is the factor, and that is our treatment. There are 3 groups. So we have the factor degree of freedoms. Degrees of freedom is 3 minus 1 is 2. We have, in this sample, there are 3 groups and 12 measurements in each group, so there's a total of 36. So we have 36 total measurements minus 1. That gives us our total degrees of freedom, which goes here. And then we just subtract to get to the error degrees of freedom. This 35 minus 2 gives us a 33. The factor and error degrees of freedom do have to add up to the total. The sum of squares from the factor is calculated. We'll use a program to do this. Calculated there. Sum of squares for error is this value. And then you add those up to get this plus this is going to give you this number right here. So these are fairly easy. The degrees of freedom are fairly easy to get. The sum of squares, let's use a program to do that because the calculations can get pretty challenging. If I give you any of these on a test, or I will give you some of these on the test, and here's how you'll calculate it, but you will not have to, you will be given the sum of squares. You don't have to calculate the sum of squares. Again, this textbook, we're mostly interested in understanding how the various tests should be used instead of worrying so much about the calculations. So, here's how you calculate the mean square. This number divided by that gives you this. This number divided by 33 gives us this. Okay? So if you're given this column and this column, then you can calculate this column, and you will be expected to do that. Now let's calculate the F value. The F value is simply this number divided by this number, and that gives us a value of F is equal to 9.47. Now, we use this value from the F and the numerator degrees of freedom and the denominator degrees of freedom to calculate the F, the P value. Some of these are given in the book, although usually a computer program will calculate those for you. But this is from the back of the book, and I apologize, it's a little bit fuzzy, but this is the 0.025 level. The numerator degrees of freedom is 2. The denominator degrees of freedom was 33. So somewhere between this 4.1821 and 4.0310, I guess. Again, I apologize for the fuzziness there. But you can see that at the 0.025 level that the 9.47 that we had on the F value is greater than that. So we know that the significance level is going to be less than the 0.025. So if we were doing this at the 0.05 level, we would accept the fact that there is a difference between the groups.
I'm going to pause at that point, and we'll pick back up with that in the next